So first example is the vertex cover problem. There are actually two versions of the problem, the decision version and the optimization version. And this is the decision version. So given an undirected graph and the integer k, does this graph contain a subset of the vertices such that the size of this subset is at most k and every edge in G has a vertex in V prime, which means V prime is the vertex cover that covers every edge. And this is the decision version. And this is the optimization version. It says that given the graph and we're supposed to find the minimum vertex cover, we're going to try to solve this optimization version. So to do local search, we must figure out the definitions of local and search for this specific problem. We must define first the feasible solution set, that is the set of all the vertex covers. And there's a trivial one. Do you know what that is? Obviously, the whole set of vertices is certainly a vertex cover, right? It certainly covers all the edges, right? So that is a trivial member of this feasible solution set. Next, the cost function. We try to minimize the size of this vertex cover, right? And now it's time to define local. Local means S prime can be obtained from S by adding or deleting a single node. So to change one node from S, and we can obtain S prime. Well, deleting is reasonable since we're trying to minimize the size, right? But why adding? Well, push this question to your head stack for the moment. We'll come back to it later. So according to the definition, we can see that each vertex cover has at most V neighbors. That's because that each vertex can be deleted once, right? And search is to start from the trivial case. We start from any feasible solution and we try to delete one node and check if S prime is still a vertex cover, and certainly with a smaller cost. That's very simple, right? And let's see how it works. Case 0, say if we have a graph with n vertices but no edge at all. So what is the size of the vertex cover? 0, right? So we start from this whole vertex set and begin to delete anyone, randomly select anyone and delete it. And is it still a vertex cover? Yes, for sure. And we can just keep doing so, right? Delete all the vertices eventually, step by step, and obtain an empty set as the vertex cover. That is the solution with the smallest size. So case 0 is extremely simple and we can indeed obtain the global minimum. Okay, and the situation is like this, a simple curve with only one minimum solution. So it easily converges to the only global minimum. Okay. Case 1 is a little bit more complicated. As a graph looks like this, we have one central vertex that covers everything. So obviously the global solution is what? Is just this vertex with size 1, right? That is the minimum vertex cover. However, if we start from the whole vertex set, and unfortunately we just deleted the central point at the first step, what's going to happen? Then we won't be able to delete any one of those remaining vertices, right? Because if anyone is deleted, that corresponding edge will not be covered. So that's impossible. It's no longer feasible. We can't delete this one, not this one, not this one. And when we finish testing all the vertices, we're going to end up at the solution like this. This is certainly a local optimum, but far from being the global optimum. So this is not the right solution, where the global optimum is actually the central vertex, right? So the situation is like this. We have one local optimum. So if we are not lucky, if we choose our initial point to be exactly here, then we are trapped here. There's no way to jump out to get the global optimum. All right, so that's case 1. Case 2 is even more complicated. Okay, it's a graph looks like this. So what is the optimal solution? This is one, right? The optimal solution contains exactly 3 vertices that can cover all the edges. However, if we are not so lucky, if unfortunately we happen to delete one of the correct solutions, what's going to happen? It's going to be something like this. Then we won't be able to delete any one of these 2 black vertices, right? If we have to keep these 2, then probably we're going to end up at a solution like this. So that contains 4 vertices, which is a local optimum but not the global optimum. And such kind of solution is not unique. We have many more ways of making mistakes, like this, right? So this corresponds to the situation like this. We have many local optimums, and it's quite easy for us to get trapped in one of the local optimums. Okay, so let's pause the video here. Try to think about more cases in which the gradient descent doesn't work. Okay, I'm sure you have found all kinds of cases, right? Now think, what is wrong with this method? And how can we make any improvement? One big problem is just like what we have encountered in the greedy algorithm. Once we make a move, there's no way to undo it. So if we are not so lucky, if we jump into a local optimum, the algorithm would stop since there's no improvement, right? So what if, even though we realize that we are at some local optimum, yet still we will try to jump out and seek some other possibilities? So that is the idea of this metropolis algorithm. Metropolis has nothing to do with the big cities, right? It's named after Nicholas Metropolis, a physicist who invented this algorithm. So this is the pseudocode. In this algorithm, there are 2 constants defined, one constant k plus a capital T. And again, we start from any feasible solution and initialize the mean cost to be the cost of this initial solution, and then jump into this while loop. What we're doing here is we randomly choose any solution from the neighborhood. Okay? For the vertex cover problem, the normal solution would be every time we try to delete one vertex, right? But here, adding is also considered. Okay, so you can randomly either delete one or add one to S and to obtain S prime and compute the current cost. Okay, if this cost is better, then we update the mean cost and update the solution and go on to the next step. Otherwise, it means if this solution is worse, it's not better than the previous one, still we might update it with a given probability. Okay, and the probability is calculated according to this function. So it's a kind of randomized local search. If we look back at the case 1 in the previous page, what is the case 1? Case 1 is when we have a graph that we have a unique center, right? So the unique center is the final solution of the vertex cover, right? And once the wrong vertex is deleted, once we deleted the solution with the original algorithm, we're going to be at the dead end, right? But here, with this metropolis algorithm, once the wrong vertex is deleted, it's still possible to add it back. So to jump out of the local trap and get the right answer. However, if we look at case 0, so what is case 0? Case 0 is when we have n vertices but there's no edge, right? And if we apply metropolis to case 0, what's going to happen? We might end up at like bouncing between adding and deleting indefinitely. So the performance of this algorithm depends on the definition of this probability, especially depend on this capital T. This capital T actually represents the temperature. Well, since this algorithm is invented by a physicist, it has some physical background. So this capital T is the temperature. When the temperature is very high, what do we get? We get a large denominator, and therefore this number is close to 0. So it's e to the power of negative something that is almost 0. So this number is very much close to 1. 1 is what? 100%, right? So that means we are very much likely to jump up. So it's like when the temperature is high, we get quite excited and easy to jump up and down, right? So when t is close to 0, this one tends to what? We have an almost 0 denominator. So that one tends to negative infinity. So e to the power of negative infinity tends to 0, means the probability is close to 0. So it will be close to the original gradient descent method, right? So it's very much unlikely that we're going to do this change. After all, it looks a bit tricky to find a proper temperature. And that's why we have this improvement method. It's called simulated annealing, 模拟退火. And the idea is like forming the chocolate. When the temperature is very high, the chocolate is in the liquid form, and it's impossible to get the shape we want, right? And however, if we drop the temperature dramatically in a sudden, it will get frozen in a sudden, right? And we still cannot get the shape we want. So the idea of simulated annealing is this. The material is cooled very gradually from a high temperature, allowing it enough time to reach equilibrium at a succession of intermediate lower temperatures. So which means that we must define a sequence of temperatures called the cooling schedule, a sequence of temperatures, and hope that it can eventually converge to the solution we need.